Welcome to our weekend Bucky call. It's July 26 or 27. Joe, how are you feeling and what do you anticipate today? I think we can hear you.
One more second.
Okay.
All right, sorry, there we go. So I'm feeling great. Had a really good day. Met a lot of nice people. So I'm at an assembly here for American Ethical Union, and we had a lot of different interesting presentations. And it's always good to engage with new people. As far as my expectations, for today is to kind of still take something away where we can link it with what we're doing with cosmometry. I really think that what we covered with the isotropic vector matrix has really kind of been pretty foundational and kind of been able to see the relationships between cosmometry and as well as Amy's book. So, Lee, how are you feeling? What would you like to take away from today?
Lee, want to unmute, Lee?
I can't hear a thing.
Do you want to unmute? Unmute and share how you're feeling and what you want. I'll turn that thing on.
Yeah. Steve? Hello, Richard?
Sorry for the technical difficulties on this end. We thought we had everything resolved. Lee, have you found your green button yet?
Yes, I did.
Well, push it again because you need to find your microphone. It's not yet on.
Where it is.
It's at the bottom of the screen. When you tap the screen, you go to the bottom. You just switch cameras, so now we can see in front of you. Why don't we, Manu, how are you feeling and what do you anticipate for today? And I'm going to help Lee get her technical stuff done.
I feel good to board the train. And I anticipate that we are going to continue on the momentum that we built in the past few sessions. And that is going to be fantastic. I don't know where we're going to land, but we are going to progress. I think, is it Richard? How do you feel? What do you expect, Richard?
Well, I'm feeling quite good, and informally, I talked about some exciting events that occurred in the last 2 days of meeting Bucky Fuller disciples from Australia or New Zealand, who've been working with what they call tetra mapping for about 20 years now, and they're celebrating the 20 years this year, and they have quite a lot of Maori indigenous people as part of their system. And so they were talking about the connection between indigenous and Fuller's work on Friday. And then today I I found the schedule that's going to for the conference that I'm going to present a 20-minute presentation on the essence of a book chapter that's just been published by a New Zealand editor, co-editor. And when I found my schedule today, I'm one of two people in an hour-long session and the other person is somebody from New Zealand talking about Maori culture and indigenous ways. So I'm being surrounded by the southern half of the world. So um, so here we go. Here's Cape Town capturing me, and across the way are the colleagues from New Zealand, um, and they. I was also mentioning that I went through the 2.5 days of presentations that are scheduled for the conference, and I would say maybe even half are all from New Zealand. It's like they moved the whole country here for a week. So anyway, I'm feeling good, and I'm feeling anxious about what I'm going to present, to be able to get an idea across about what we've been discussing and using Fuller's work and David Boehm's work, and so like you, I'm expecting to get more and more sort of on track, if you want, exchanges and understandings coming out of our readings of Amy's Fuller explanation book. So,
Excellent.
Cool.
Lee, are you now on the
I
air?
am
And how are you feeling? And what's
online.
your expectation for today?
I am feeling quite well. Great, in fact. And I have all kinds of expectations for tonight's. We had difficulty last week. I couldn't hear anything. And so I want to find out what happened last week and possibly find out more today. So that's going to be fun. And I pass this to Manu. How are you feeling? And what do you expect? Manu?
Thank you, Lee. Yes, thank you, Lee, for me feeling twice. I feel good. And I say I was happy to be on the train, and that we continue on the momentum that we built a few weeks already, and that we learn wherever it is. I know that we're going to learn having grown and on the land of growth. So, Steve, how do you feel? What do you expect?
Very good. Mute your phone, please. Okay, I'm feeling pretty good. I'm going to hope that Lee mutes your phone so that there's no echo. If you could mute your microphone. Good. Well, one day we'll have it figured out over here, and I think I can talk if I don't listen to it. So I hope the echo is not too bad for you guys. I do notice that we got a WhatsApp from Anne, and she wanted to text earlier one of her teachers, and she'll join as soon as she can. One of her teachers is doing something. Oh, she's at a funeral.
Right.
So, and she'll do something. And as soon as you can find your microphone button, it would be helpful.
I have been hunting.
So anyway, I'm just on this journey with all this spatial stuff. I just am really profoundly touched that's a lot of the artifacts that I witness every day, like gravity, is just an artifact of the shape of space. And that blows me away. So I'm looking to see what else I can learn. Some of the stuff we're talking about today, we've talked about before, but I didn't understand it then. Let's hope I understand it today. And we're ready to go. So I can throw up the reading here. Joe, how soon are you going to land on your computer, do you think? Maybe Joe is not going to be with us for a second.
Yeah, it's hard for me to tell because I'm gonna lose you here in a minute.
All right.
So whenever the next train comes, and I should be, I don't know, about
It's okay.
yeah.
No rush.
I'm doing the best. I'll do the best I can. It's good to see you guys.
Cool. I'm in a situation where I've got this annoying echo. If I take this microphone off, I don't know. You have to wave at me or something. I'm going to go ahead and start reading. And then when you guys are ready, anybody else can read from here. But we're on page 165. And we're starting off, we're in the chapter called Multiplication by Division in Search of Cosmic Hierarchy. And this is particular volume, direct comparison. Before looking for more, are you guys hearing an echo?
Yeah.
I'm off.
Yeah. Okay, you're not off, Lee, you're still on. Does somebody else want to read while I resolve the problems over here?
Yeah,
I'll just listen over there.
I'm finding which one? It's chapter 10, right?
Or Zoom? No, you don't want to go
What's
to
the
phone
figure?
mode here,
We're
Zoom.
near figure.
There you go. None. Okay, there you go. Now you touch here. There's your microphone.
Oh, okay. So I've got the page in my book as well. So
Can you see
want-
it?
yeah, I can see it and I can read it from either my page or
Okay,
the
good.
screen. So volume direct comparison. Before looking more closely at volume ratios, we review the following mathematical generalization. No matter what unit of measurement is employed, the volume of any container is mathematically proportional to a typical linear dimension raised to the third power. This means that if we have two geometrically similar polyhedra, one with twice the edge length of the other, the larger will contain exactly 8 times the volume of the smaller, which is 2 to the third power is 2 times 2 times 2 is 8. My own little margin note here.
Yeah.
Having the same shape, the two systems will share a common constant. To bring this mathematical law into experiential grasp, we consider two familiar shapes. It's easy to visualize that a cube of edge length 2 of 8 unit cubes, 10, 2. Now imagine a tetrahedron of edge length 2, observe in 10, 3, that just like its cubic counterpart, the latitude of a two-frequency tetrahedron is 2 times that of a unit tetrahedron, and similarly that each face subdivides into 4 unit triangles. The latter observation indicates that the area of the large tetrahedron's base is 4 times that of the small tetrahedron's unit triangle base. Emulating the approach employed by Loeb in his contributions to synergetics, we can deduce that the following simply by utilizing traditional geometric formula. Let volume and what's that? Volume T and volume, I can't read that one.
Frequency.
On frequencies. Represents the volume of the large two-frequency and small unit-length tetrahedron. A plus A, the areas of their bases, and H plus H, their altitudes. According to the formula, volume of a pyramid is constant times area of base times height. And then we see the formula. And since we observed in 10-2b that the base of the large tetrahedron is divided into 4 triangles, each of which is equal to the base of the small one, it is clear that A is 4A. Again, it's, what is that one again? Similarly, the altitude of the larger pyramid is twice that of the smaller, or H equals 2H. substituting, we have the volume.
Lots of math.
Yeah, so
No,
volume is
it's just simply there. They have deduced what we've always known. If you take one big tetrahedron and you do the first derivative, you have 4 tetrahedra on the 4 corners and an octahedron in the middle.
right.
And we know that the volume of the octahedron, because we did the division by half on each edges, is equal the sum of the 4. So 1 octahedron is 4 tetrahedra. So the total volume of the maximum tetrahedron is 8. 4 plus 4. That's what is demonstrating there. Do you get my reasoning?
Yes. Do you get it,
Okay.
Richard?
Yeah, it's just
And Lee, I want
I'm short on the symbols.
my target is Lee. Can Lee see? No, I'm serious. I will show her.
You turned
Let me
off your video, Lee.
Can Lee look, please? Okay, Lee. Can she look, you see?
I'm gonna make sure she.
Yeah, please. Because that's an important test here.
Oh, that's big T and a little t. Okay.
Yes. Lee, can you see? Can you see what I have in hand?
Yes, I can.
Okay. Can you see that this thing is a big tetrahedron?
Uh-huh.
Okay. Now, can you see the division? Can you see the red line, the
Yes.
blue line, and the green line?
Uh-huh.
Okay. So the whites that are at the edges here, they are also tetrahedra, right? Small tetrahedra.
Uh-huh.
How many are they?
1, 2, 3, 4.
Okay, look, Lee, look, don't
Four.
think.
Tetrahedrons.
1 on each
Yes.
corner.
And one
Yes.
on each corner.
Has one.
Yes.
And
So that is 4. Now, we've
No.
always talked about the implied octahedron. That is the volume that is included within this line, the red, the green, and the blue. Inside, it is implied where my fingers are.
Uh-huh.
You see where my fingers are. You see my 2 fingers?
You're in the middle.
Yes. There is something there that is in the form. Steve, can you show that your figure that you usually show, Steve? Yes.
Even inside of there.
Inside
Yes.
is an octahedron.
Yes. There's something there in the form of this.
That's right.
Octahedron.
Yes. Inside there. If you look at it, normally Steve have one that you can see because it open like a mouth and you insert it inside. Okay? So
Okay.
the volume, yes. Steve, can you show that? It's very illustrative.
Yeah,
Exactly.
I've been showing it to her as you've been talking, and I took my
Yes.
octahedron out of the center. And the thing that you
Yes.
said, Manu, that was catchy for me was that because I'm dividing each of these edges in half,
Yes.
I take my one tetrahedron, I end up having 4 separate tetrahedron, but inside is an octahedron. I know this is still equal to all of this because this is half of a big tetrahedron.
Yes. Yes. Yes.
Therefore,
Yes.
it's there's 4 tetrahedra, and it's equal to 4 here, so that's 8 when we put them all together.
Exactly. Yes. That's what algebraically he was demonstrating there. Fine. Okay.
Good. If we're ready to proceed, we will proceed. Did you get anything out of
Yes.
that, Richard?
Yeah, it's just it was hard to read the formulas, but
Yeah, it's very hard.
This was better, and I think it allows us to actually jump right over to the next section, multiplication by division.
Okay,
Exactly.
So multiplication occurs only through progressive fractionation of the original complex unity of the minimum structural system of universe, the tetrahedron. Instead of starting with parts, points, straight lines, and planes, and then attempting to develop these inadequately definable parts into an omnidirectional experience identities, we start with the whole system in which the initial point inherently embraces all of its parameters, all the rules of operational procedure are always totally observed. I have to go back over that because as soon as I see multiplication by division, I immediately go to my understanding of midpoint division of a triangle. So then we go to deeply impressed by Arthur Eddington's definition of science as the systematic attempt to set in order the facts of experience. Fuller constantly sought meaningful organization for groups of experiences or events. Multiplication by division is one such effort. Events, of course, include structures and almost everything else. In energetic scenario universe, things are events. Essentially, multiplication by division derives volume relations through the straightforward logic of direct observation rather than by rote application of traditional formulae, which leads us through awkward values before revealing the underlying simple relationships. As we'll see below, this direct observation is accomplished by comparing given polyhedra to the unit-length tetrahedron. So the tetrahedron is the starting point. Fuller's organizing strategy begins with the tetrahedron because as the topologically simplest structural system, it is a logical starting point. Consistent with this emphasis on whole systems, the ultimate reference point is, in synergetics, is universe. The tetrahedron thus acts as an appropriate whole system for the procedure described below, in that it is the first finite unitarily conceptual subdivision of universe. More complicated systems are developed through subdivision of this tetrahedral starting point, so that a progression is contained within and organized by the whole. In respect to such a scenario, universe multiplication is always accomplished only by progressively complex but always rational subdivisioning of the initial simplest structural system of universe, the sizeless, timeless, generalized tetrahedron. Onward.
Can we stop there?
Yeah, because this is
Yes.
so much deeper than the simple explanation of multiplication by division with triangles and tetrahedrons.
Okay. Let us come to another basic. Let's look at universe. What is a verse?
Tell us.
A verse is a statement, an explanation, a naming of something of unit in literature. Like in the Bible, you have verse 1, verse 5, verse 10 of a book is a statement. The verse is a unit statement in the narrative of a story. So you go from verse to paragraph, and from paragraph to pages, and from pages to text, continuing. All right? So universe means what? Uni dash verse. What does uni mean? One.
All verse.
Yes. So it also means our common interpretation, our one interpretation of what surrounds us. Universe. Because universe is understood as universe by all those who dwell in universe. Now, if you take that, how do we understand what surrounds us? By rationality. Ration means dividing by something that we can recognize. A ration. My daily ration of food is 2 kg of this or that or that. It is a proportion. So universe, by definition, is rational. That is, it is structured. It is very important to understand that a structure is a set of rational measurement that close. That's another definition of what a structure is. A set of rational pathways of energy that loop. That is a structure. So
yeah, that's fine, but we're reading multiplication by division, and we started out just a minute, and we started out that it's fractionation, or it has to do with fractals, and as I said when I first started reading it, I have my own margin note about multiplication by division in a fractal sense is simply dividing at the midpoints of a triangle, and you get multiple triangles. That's all. Even the way she's explaining it right now, and perhaps even yourself, it seems to be taking the long way around to getting at the midpoint by midpoint definition, which is fractal.
It means I didn't explain well. You always starting everything that we know at the simplest by taking a linear segment that you can identify in a phase, divide by 2. That's the beginning of everything.
That doesn't work.
No, Richard, listen to me well. You don't discover the triangle innately. You discover the triangle by taking one segment related to the other, That's already complex.
I find that I can discover the triangle in a tree trunk or a tree trunk.
Because you are used to the pattern. You're forgetting what you call pattern. Take a baby and tell me if you discover a triangle. Take a baby. You discover a triangle by experience.
Well, keep going. I mean, again, where are you going with this to get to the section on multiplication by division?
Yes, exactly.
Okay.
I'm saying that the whole of universe is a whole. It is, let's just say, the tetrahedron is the figure in which we are. The only way that we can reconstruct it, it is by taking rational pieces of that and concatenating them to make sense of a whole. The concatenation, that's one piece on the other to make it a whole. That is multiplication by division. And you always start, let me explain it again. Let me explain it again. Let's just take this structure that I am. And I take my pen. I'm a human into this. The top of my pen or the base of my pen here. I have 2 eyes looking into one direction. That's how I perceive things. If I look in whatever direction here, the first thing that I perceive is not the window, it is the blue. It is the edge. It is the boundary. That's the first thing that I look. Because this is a solidified flow of energy at high frequency to make it specific for me to see. So I'm not going to come naturally and start taking at once the green, the blue, and the red and dividing by 2. It doesn't make sense. What I decided.
We don't divide by 2.
Hold on, Richard. What I do is that if I'm here in the middle, I'm in universe here, I look here, I say, okay, this segment, this blue thing that I see here is of length this, is something that appears to be in amplitude this thing. Therefore, as a baby, I can take that thing that is pliable like this and fold it in such a way that this edge and this edge come together. Then I realized that the length of the resulting fold, like this rope, the length of this diameter of this is half of the length of this circumference. That's the way that's the rational way of doing. You start by dividing by 2. That's why everything that is geometric.
That is not what multiplication by division means.
That is it, Richard. That is exactly it. We can rest that and ask
Okay.
the mathematician.
So let me just say
And I
this.
will bet $100.
Well,
That's what it
good.
is.
I want $100. But as I look through the face and I see the edge, here's the edge. And what I do is I break it in 2. And now I have
Exact.
divided, and that now I have 2.
Yes.
And so I multiplied because I divided. I think that's
Yes.
what Manu just said.
Yes. And you see, what you see, Steve, further to what you say, what I say is that what you first see, if you are non-initiated in the
Right.
mathematics of things, you first
You
see
see a
first the
line.
segment. Yes.
Yeah, you see a line segment.
Yes.
So I'm going to now divide it again. Now I have 3.
Yes.
So I have multiplied now and I have 3 because I took my one simple segment and I divided it into 3 parts instead of 2 parts.
Yes.
Right.
And then now you start folding, Steve.
Now do one more thing. Take those 3 and turn them into a triangle.
There we go.
But that is complex,
right.
Richard. That is complex.
Just hang on.
Hang on,
Yes.
though.
So that we can both get to the same kind of answer. So put the triangle the way you just made it.
I will.
So you divided by 3 times, and now you got 3.
Yeah.
Now you create a triangle. Now you don't have the piece right now, but go to the midpoint of each edge.
I do. I can go to the midpoint of each edge.
Oh, okay, good.
I'm deliberately designing this in a way that will teach this model.
Beautiful.
There we go.
And so what have you got?
I have 4.
Right.
4 triangles
But
because I divided
you did
by
it twice.
2.
You divided twice.
No, just hang on. Just listen.
No, I've listened to you, Richard. Yes, continue.
Well, it's like the first one sort of shows how you break it out and you get 3. Then when you can turn it into a triangle and you do the midpoint, and you go from 1 triangle to 4.
Okay.
So that to me that's the simplest, clearest example of multiplication by division.
Good.
So you divide at the midpoint.
Hey, Manu, don't shake your head
get
though,
4.
because
No, I just say I'm shaking to say we disagree. You know, I have a right to say that I disagree.
Well,
Well,
you
do
can't
you see
disagree. You can't disagree
Yes, I
with
can
the
disagree.
experiential evidence.
wait,
No, you can't,
Manu,
because
do
there
you
it
see
is. There's
4
proof.
parts here? Do you see 4 triangles here?
Yes, I see
All
4
right, well
triangles.
then that's what Richard's saying.
No, but to arrive at 4 triangles, you did twice the division. It's not the simplest. You divide twice.
No, I
Actually,
didn't.
Whereas
divided 3
to arrive
times.
at the first one, you divide just once. You multiply by 2 by
Yeah,
dividing
when
once.
okay, you're right. When I do, you're right about the simplest form of manifestation. You're absolutely right. However, I'm not dividing by 2 here. I have to divide this thing 3 times to get my 4 triangles.
Exactly. Because
One
it's a
here, one
surface,
there,
Steve.
one there.
Steve,
Well, of course.
you are dividing, hold on. You are dividing a surface. If you divide the surface, you start seeing Bucky's formula, where you have frequency square. 2 to the power of 2. Yes. That's the way you discover inductively a general formula. That's exactly what
Manu,
Richard is doing there.
Exactly what you're trying to do. You understand this very well, and what you're not doing is listening to how Richard's brain is parsing this out, because you're actually agreeing.
No, Steve, you're not correct there. I'd listen carefully. I repeat carefully to Richard.
Yeah, but
The only point of disagreement, the only point of disagreement with Richard is that yes, it's multiplication by division, but it's not the simplest. That was the point of the argument.
But
I-
Richard
no,
wasn't
but
arguing.
you missed the
he wa-
point. I didn't say anything about the simplest.
He
I
didn't say
simply
anything
said,
about the simplest.
So why were we arguing that? Why?
well, because I said that my image of multiplication by division is you take a triangle and at the midpoints, you connect them and you get a multiplication. You get 1 to 4.
Right.
I didn't say anything about simplest. I just
Yeah.
simply said that.
Richard, you started the discussion because I say, hey, yes, is that, but it's not the simplest. That's why
but-
the discussion started.
Well, I
But-
didn't say anything about the simplest.
Right. You're
Okay,
the one who
so-
brought
so-
up simplest.
I
and
just
nobody
said
I'm
else
sorry.
this-
So I'm
Nobody
sorry
else
to
was
waste
interested.
everybody. I'm
Don't be
sorry to waste
sorry.
everybody's time.
Don't be
So let's
sorry.
continue.
Don't be
Yeah.
sorry. Just acknowledge that no one was interested in the simplest. And by you breaking it out and making it simple, you added a dimension to it. But that does not invalidate Richard's point over here. This is the simplest.
Steve, nobody should lend me any word that I never used. I never invalidated Richard's thing. He read a text where Amy went in a complex way to explain something through formula. We came to the method of discovery by observation and by doing. And the simplest operation was that is divide. She said a general thing that every proportional complexity is derived through a division. That's how you have multiplication. Multiplication also means complexity. Because you take parts that are many and then you put them together to make a sense. That is complexity. So that's what she said. And Richard explained that you understand it, that the simplest is by triangle. I say, no. The simplest is not by triangle, is by, if I'm in a system, what I see at the time is a segment. It's not a triangle.
Richard never said that it was the simplest, that he never saw, he didn't say anything about how simple
No,
it
he
was.
says so. He says so. He says so.
No, he said he started from
yes.
Let's stop there. Manu,
yes.
Manu,
yes.
He said that when he's already approached this problem, he's always approached it from the point of a triangle. He's never approached it from the point of a line segment. So
but he was saying, Steve, he was saying it in interjection to what I was saying. And I say that if I'm in a system, the simplest thing that I see is a segment. That's what I say.
But that's not what the book says.
No. I don't agree to that. Don't try to put the problem onto me. The problem is on Richard.
No, the problem is in the book. It's in the book.
No. We read the book all, and then we're trying to find a simpler way.
No, we aren't trying to find a simpler way, Manu. You wanted to show us the simpler way.
Okay, I'm not showing anymore anyway. Let's continue. That's great.
The simple way you're showing me is wonderful.
No, it's not. It's not valid. It is not valid. I agree. Let's continue.
It is valid.
No, it's not.
It is valid. Yeah,
it's not.
Don't discount yourself.
No, I'm not discounting myself. I'm just saying in the context of this discussion, it's not valid. And I have a right to say so. Because we are going to something. I was trying to think that we are simplifying. And Richard said, I'm complicated. I'm complicating it. And you agree to it. It's not correct.
Richard didn't say you were complicating it.
Okay, so let's not waste time on it. We're wasting more time.
Yeah. The issue was never which is the simplest and which is more complicated. That was never a part of the conversation. And I appreciate you bringing up a simple way to look at it. So I took your words and I took my little magnets and created what you said. And that was very helpful for me. So, Richard, where are you at this point, Richard?
Well, we started with multiplication by division, and we got down to the bottom of tetrahedron as the starting point.
Okay.
And
shall we continue from there?
And the first part of the next section is onward. So that sort of sounds like Manu saying, let's move on.
Okay, good.
So we seek to develop a variety of polyhedra through subdivision of the whole. And in so doing, provide the experimental evidence to verify the results shown in Table 5. Where's Table?
Is table 1 in my book? It says table 10.1, which is up here. Oh, crud.
Okay, well,
I'm afraid to get this too out of control.
but anyway, that's
I can show you table 10.1. It's right here.
oh, the tables. Yeah, yeah. No, we don't need to.
There's table 10.1. That was several
Right.
pages ago.
Yeah.
Yeah.
We can imagine a single regular tetrahedron and then bisect each edge to create the two frequency tetrahedrons shown in figure 10.3. One by one, we remove a single frequency tetrahedron from each of the four corners, unwrapping the hidden octahedron. Okay, we've got that pretty much in our heads, at least I do now. Chopping off 4-unit tetrahedra subtracts 4 units of volume from the initial total of 8, the value determined earlier for a double-edged length tetrahedron, indicating that the octahedral remainder has a volume of exactly 4. In other words, an octahedron has 4 times the volume of a tetrahedron of the same edge length, we thus begin to derive the values in Table 5. So again, we've gone over this whole question of the volume, and a volume of 8 is made up of 4 in the octahedron and 4 of the surrounding tetrahedrons. Is that correct? I understand it to be correct. And so, as we said at the end of this chapter, or this paragraph, an octahedron has 4 times the volume of one tetrahedron of the same length. We thus begin to derive the values in Table 5. And then we go on to the cube. But I guess, like, again, for me, because we're starting with the tetrahedron and we're not starting with just a line, what comes out in that paragraph for me is when it says we bisect each edge to create the 2-frequency tetrahedron.
Right.
And that gets me closer to how I've become to understand what I call it, I guess I call it a simple way of understanding multiplication by division. I'm not saying it's the simplest way. I'm saying it's a simple way for me to capture the idea of multiplication by division, and it's bisecting the edges,
You betcha.
which is when I think back on what Manu was saying earlier, talking about lines, it is the dividing the edge by 2. Bisect, I'm sure, must mean divided by 2. So in that sense, I think we're coming to a confluence of understanding. And he started off by wanting to take it down to the line and bisect a line. I was working with the tetrahedron in part because the literature that I read, and we're now reading again, starts with the tetrahedron as the simplest structural division of the universe.
Yeah.
And so I'm starting with the tetrahedron, not with a line, that's all.
Yeah,
But I
perfect.
think we have bisect in common, and this way of multiplying by dividing is a new and helpful way for me to understand what I understood through a different kind of way of calculating and understanding fractalation, because the thing that really is important to me in terms of the fractal part of all this is that you use the simple formula of bisect at the midpoints, and you can do it forever.
Right.
And And that to me is what fractal is all about, is you
Right.
use a simple formula to derive something that ends up looking very complex, but it got there through a simple formula.
Right.
Yeah, so
Good.
I appreciate this kind of dialogue to kind of work through this. But I don't know if we want to go into the cube part now, or there's
Well,
more
I'd like to
to
comment.
talk about.
I'd like to comment for a minute, and that is that this is the what Manu was showing us right off the bat. Here's your tetrahedron with the four corners chopped off, and what's left inside is the octahedron.
Right.
And this is not as clear as the model that Manu was showing, and that Manu helped me build several years ago, which I was holding on to as well. This guy right here. And there's an octahedron inside of there, but I've taken it out. I even started numbering all of the faces on these octahedra, and then put similar numbers on on each of the tetrahedra that are here. And I numbered all the faces, and then found the numbers and matched those numbers on the octahedron up to the numbers of the faces inside of it. It's really cool. And having dealt with this for a while, I have a sensibility about it, but not a verbal understanding. The words in this book are still confusing to me a little bit, although I think I understand the concept. So, yeah, the
Can I
book
say
wanted
something?
me. Yes, you may. I would like to say one final thing, and
Okay,
that
go on
is,
before I say it.
thank you. And my point is that this book started out with the tetrahedron as the starting point. Manu was kind enough to show us as the line as a line segment as a starting point. That's
Right.
where the conflict came in, because we've all been reading about this and trying to understand this from our points of view. So thank you for bringing up a more simple way to look at it, at least in a two-dimensional reality with a line segment. The tetrahedron is 3 or 4-dimensional, and so it makes it a little bit more comprehensive. And I'm ready to do cube when you're ready. Manu, what is it you want to add into it?
Okay, do you see this?
Yes.
What is the dimension of this?
Well, it depends on what your unit of measure is. It's either 1 or 3.
No, it's only one.
Okay.
This
But
guy is a one dimension, is one segment, is one line.
then why is it red and green and blue?
It
Why
doesn't
isn't it
matter.
all red?
No, hold on. Just this is one. Okay. Now, if I do this, how many dimensions?
2.
Exact. So what is a dimension?
It's a direction.
Is a turn. Is an angular turn.
Okay.
When you say in the folding and unfolding process, one dimension is where you fall. Now, let's take this one. Let's do this. How many times have I unfolded?
You still
Have
have
I
one
turned?
dimension.
How many times have I? Let me repeat.
2. You
Two
did
times.
2 folds. You did 2 folds.
So what is the dimension of a triangle?
You're
The
still in
way
2
you're showing it,
dimensions.
2 dimensions.
You're still in
Exact.
2 dimensions because your turn has to be
No,
in
hold
90
on.
dimensions.
Yes. This is one dimension.
Right.
This is
But when
something.
you turn it at 90 degrees, it's 2 dimensions.
Yes. This is not something. It doesn't hold anything. This whole
Right.
energy, that guy doesn't hold any energy.
Right.
We are in a real world where we hold energy, we hold something. The only thing
Yeah.
that is around is energy. So I turn like this, that's one dimension.
Right.
In order to close, I need to turn a second time. Then I
But
hold energy within this.
But that's still only 2 dimensions, right?
Yes, it is 2 dimensions. That's exactly my point here of explaining. the notion of dimension and turn or division. Because you don't cut for it to stay like that. You cut something in order to bend it into something. I cut something. If I want to build a stud on something, I cut a piece and I put it to make the stud to hold like this, so that this thing is pushing
Yeah,
here.
that's fine. Well,
and
just go the next step and turn it into 3 dimensions.
Please.
Okay, I need to turn again once. I need to find a way of cutting a piece of it. Let me take the color. How many colors here? Where's my yellow? All the yellow is used. Well, let me take red again and put it here. I need a third. And because I've done this, and that there's a principle of duality, if I do this at an angle, naturally, this guy here and this one we want to link. They will do 1, 2. They will cut. Now you are cutting a surface.
Go ahead and do it.
No, it's done already.
No, it isn't.
Yeah, it is.
That's not
Richard would like to see
three-dimensional.
the tetrahedron be built.
Yeah, this is 3 dimension. This is 3 dimension. This is 3 dimension.
It's 2 dimensions.
Well, no,
It's
it's
3.
actually 3 dimensions, Richard, because
Richard, it's 3 dimension.
yeah, but it's 3
Yes.
dimensions because the triangle is in 2 dimensions, and when you add that other turn on it and it sticks up, it becomes a 3rd dimension.
Yeah.
All right,
This
go
is
ahead, do that. All right.
This is 4 dimensional. Okay. And it
Why is
leaves.
that 4 dimensions?
Yes. And it
Why?
leaves. Well, it doesn't close. If I put this, let me show you. If I put this
Yeah,
like this, there's no motion. It's dead.
but it's 3 dimensions.
Yes, this is 4 dimensions. Dead. Universe is just the IVM, the isotropic vector matrix. Here, it's dead. It doesn't go anywhere. Within the universe defined by it. I need to leave a degree of freedom for this guy to move and form other associations. Very important. You never talk about a triangle without talking about a square. Never. The two go together to form our dynamic universe. We saw it. It's a principle. Never, never.
Well,
You make
I
a
can-
triangle. If you build something, if a triangle is a matrix, it's dead. A matrix is dead. A matrix, the definition of a matrix.
Okay, just go back to those angles and create an XYZ coordinate.
Yeah. This XYZ.
Right. And how many dimensions is that?
3.
3, right.
Yes. In order for me to have a 4 dimension, I need to add something, that curve again,
That's right.
to close it. This is 4 dimension.
It's not closed yet. It's not closed.
No, it doesn't need to be closed. It just needs, dimension means you fold in a such way that anything that is within it can be explained in rational ways.
All right,
You can describe a pathway to get to that
Close
point.
it. Go ahead and close it.
Okay, if I close it now, it is dead. This guy doesn't go anywhere. This tetrahedron is dead in terms of energy motion.
Doesn't matter
All
what it's
energy
dead.
that is here doesn't go anywhere.
Doesn't matter to me at this moment is in terms of the dead part. We can get to that. But how
No,
many
it's-
dimensions
hold
is
on.
that? How many
4.
dimensions? But
4.
So you went from 4 to 4.
No. This is 3 at 90-degree angle here. It's 3. If I close here, it's 4. Remember that a dimension is a curve, a break that you take onto a pattern. That's what you call a dimension. You talk about the surface, the second dimension is the
Yeah,
depth.
well, just hang on. Now this is what Bucky helped me with, is that when you end up with that, and you started off from the 3-dimensional coordinate system, XYZ, 90-degree angles, 3 dimensions. That's what we all understand. But when you put the observer into the 3 dimensions and close it like you just did, you get 4 dimensions, and you get the observer involved with the XYZ coordinate system, only now at 60-degree angles and not 90.
No, it's no more XYZ. It's
Yes, it
XYZ.
is.
No. Here, look at. Hold on.
Jesus.
This is another tweak of it. Let me take this white for you to see clear. If I'm the observer inside here, I see through one window.
I'm not
2
talking about
windows.
the observer inside. I'm talking about the observer at one of the points.
But
Which-
this is a point inside. What do you call the point of the system?
Well,
Is
just
what-
let me go back to what I got taught from Bucky's Tetrascroll and talking about the Trinity and the observer, the Goldilocks looking at the Trinity, the 3 bears. And when that got closed, that's when Bucky was talking about 4 dimensions that involved the observer and the observed. So
Okay.
that's where I'm
Is this
coming
close?
from.
Is this the Tetrahedron close or not?
That tetrahedron, in my mind, is close in the sense that it has both inside and outside to it.
Okay. So if it close, everything that is inside it is both the observer and the observed. Inside it, you can see all the twists of this system.
Manu, all I'm trying to say to you is that's not the diagrammic kind of description that Bucky gave in Tetrascroll. That's all.
That's it. That is it.
What?
That is it, Richard. That is it. Or we didn't read the same thing. That's exactly what Bucky was explaining.
No,
Bucky
it
said
wasn't.
that.
No, it
in the
wasn't.
No,
Tetrascroll
hey,
book.
Yes.
You
Wait,
look-
listen
look-
well. Listen well.
Yeah,
Bucky
okay.
said, if a system is a tetrahedron, yes. Steve, don't show. Hold on. I can write 1 million volume of this, telling stories, but to one effect. If I'm inside here, in order for me to see the whole of this world, Steve. Okay.
What? Okay, what, Manu?
If I'm inside here, in order for me to see this whole world, I need 720 degrees. I need 4 windows of 180 degrees each. That's what it is called the 4 dimensions. In order for me to see the whole world, I need to turn 3 times or 4 times. I need to look through this window, then turn 60 degrees, look this window, then turn 60 degrees, see this window, and then turn 60 degrees, see this one. So the notion of whole and phase and frequency are intimately linked. And you cannot understand the whole, that is the multiplication, if you don't understand the phase, that is the division. You cannot. That is the basic of
All I am
mathematics.
trying to say is that what you've just described maybe is certainly a way to look at it, because I've also had this kind of struggle too, in that when I understand the inner part of a tetrahedron, then I get more dimensions or more connections out to the outside 4. So that's a different kind of way of understanding.
A dimension
Now,
is not the
because-
connection, Richard. A dimension, that's exactly my point. A dimension is not the connection. They are linked,
I
but
didn't
not.
say it was.
No, but what is the point of the discussion? That's the problem
Why
I have
don't
with
you
you.
just listen
Every
for a
time
sec.
we get into something to understand, then you say and you take us back. We've progressing here. You talk about the Tetrascroll or whatever, and the observer and the observed are in. That's what you talk about. That's exactly this. This observer in white, that is the observed, is the word. And the word is the tetrahedron. You need 4 windows to do that.
I understand what you're saying,
So
Manu,
if you
but-
understand that we progress, no, I don't want to waste my time. To be truthful,
Well,
I don't
then
want.
fine.
I don't want to be. I don't want
Then-
to be disrespectful to you, but I don't want to waste my time.
Well, then you're being disrespectful to me.
No. I mean,
but
that's
let's look at the
disrespectful to a certain
let's
point.
look at the
If every
tetrascroll.
time you come back to the same thing, I read this. We have to progress. Becky was 50 years ago. Becky died in 1983. There has been a lot of progress from Becky. I'm sorry to say it. Becky found Einstein. Einstein was older than Becky. So the progress that Becky did was only the progress of a limited being. We can progress
you
on what
seem-
Becky said.
Okay,
Manu, you
okay,
seem to be-
just
Yes,
Manu,
I'm really irritated now.
Yeah,
I said,
you
I put
are
a point.
lacking
I'm not being
patience.
disobedient to Becky. We
You're
can progress.
lacking patience.
No.
with
I've been
others
patient
on the
enough
call,
because
Manu.
Steve,
Be
we are
patient.
going to the same point every time.
Breathe.
Every time. Let me say something, and then I finish, and then probably I shut up for the rest of the call. Every time that I try to bring something that I think makes us progress, Richard always goes back and say, "But this is what I read in 50 years ago." Fuck it. Einstein read things 50 years ago and then makes a progress, a break. That was a phenomenal progress. I shut up.
So,
Okay.
Manu, build the bridge.
No,
build
I
the
build the
bridge.
bridge. I build the bridge enough. You don't
I'm
want
telling you, you did not build a bridge. What you're
No, I
saying
did.
is that's 50 years ago, and this is now, and it's new. And all
No, I
I'm
haven't said
asking
so.
you to
No,
do
I haven't
is to
said so.
breathe,
No.
be
That's again.
respectful, and
You hold on,
allow.
Steve. You are again saying something that I didn't say. I say that the repeat of the same criticism over time is tiring. That's what I say. There's what you call
But
any
it's tiring on our end too, Manu, because
Okay,
our
so
understanding is over here,
No,
and you
then I
keep
shut
beating
up.
this drum
shut
over
up.
there.
Read. Okay, read. I'm tired of being this.
It's as
of
tiring
being-
to
no.
us to have you argue with us as it is for you tiring to
No, I'm
listen
not
to us.
arguing. I'm not arguing. I'm
What
shutting
is
up
all
now.
this energy?
Shut up.
What is all the
Okay.
energy, Manu? It sounds like arguing.
No, it is. I say enough is enough at one point. That's what I say.
Manu, as soon as I say the word no, I'm arguing.
Okay,
What I
good.
want to do is cultivate saying yes.
No, I cannot say yes to something that I see is patently inaccurate. I cannot say so. I cannot say
Okay.
so. I cannot say yes to something. We have to be big enough to take the punch of an argument when it is necessary.
We have
That's
to
my
be big
point.
enough to allow everyone to have space.
No, I allowed. Steve, I allowed. You are the one that said I didn't allow anything. I shut up here, Richard talk. But every time that I bring something that I think it is improving, Richard come and say, no.
No, it isn't every
that.
time that Richard comments. Do not blame it on Richard.
No, I'm not blaming. Okay, I blame it on me. I blame on me. Let's shut this paragraph like that. I blame on me.
Okay.
Continue on the queue.
Yeah. Well, we're reading Edmondson. If we were reading Manu, that would be a different conversation, where Edmondson could contribute to Manu. But right now we're reading Edmondson, and we'd like to continue contributing to Edmondson, although it's 50 years old. So let's continue to read then, shall we?
Sure.
Well,
Okay.
let's in the sense of getting things correct, I'd be happy for us to go back and, first of all, get the Tetrascroll story correct in terms of time. And that story was told to Bucky's daughter, Allegra, when she was quite young, around the age that you would be reading things like Goldilocks and the Three Bears to your children. And if she was born in 1927, and let's say she's 5 years old when this was done, and you take, well, even just to make it simple, if you take 1930 to 2000, that's 70 years, and you add 25, that's 95 years. So the factual comment is that that story is 95 years old. And if I'm following Manu correct, it's like that's old knowledge. It's no longer correct. And what he's trying to explain is something that is more relevant in terms of progress that has been made. I can accept that. But all I was saying is that I got to understand 4 dimensions and the observer and the observed out of Bucky's Tetrascroll Goldilocks story in terms of the little girl standing looking at the 3 bears in the sky. And Bucky walked us through how you got from 3 dimensions, like we always experience right now. We experience 3 dimensions, height, width, length. And he showed that if you close it down or include the observer, the little girl, you then end up with a 4-dimensional sort of experience. And that 4 dimensions is in basically the shape of a tetrahedron. And so I'm saying that's how I learned about 4 dimensions and the observer observed, so that you move 3 dimensions into 4. And if there's something that's happened between 1934 or 5, let's say, 90 years ago, that has changed the way in which we understand, then I'm open to that too. And I have been looking at that in the sense of just the way Manu has been describing the tetrahedron, the 4 outside points, and then the observer inside. And that to me is an advancement, if you want, on understanding the observer in relation to, let's say, one's environment, or the observer in relation to the 3-dimensional surroundings that we're in. So yeah, I'm open to that. It's just I'm coming in from how I've learned things. And maybe what I learned was correct at the time I learned it, and maybe now it's no longer correct. That's certainly, that's a sign of progress in all kinds of situations.
This book was published in 1975.
Yeah, it's published in 75, so that's 50 years ago, but the story itself was told in the 30s.
Okay.
And it was just his way of trying to help his little girl understand observer observed, and I think understand the shift from 3 dimensions with the observer separate, and turned it into 4 dimensions with the observer as part of the dynamic, if you want. So
Cool.
That's where I'm at with it.
Okay, good. So Anne, how are you doing? Glad you made it.
Yeah. Yes, thank you. Yeah,
How
I
are you
went
feeling?
for
We're going to start reading again, but check in and tell us how you're doing and what you expect for today.
I'm glad to be here. There was a bit of news that came in last night, so we went to visit my teachers, one of my teachers. She's been with me for so long, So anyway, I'm glad to be here. And to also be able to catch actually the energy that just showed up just now, right? So that for me is part and parcel of I know what we do within the our Bucky group. Yeah, so I always do appreciate both ends, and so thank you. Yep, that's how I feel, and looking forward to the next maybe 40 minutes.
Cool.
Yeah.
Well, we're about to read about a cube, and so we will examine the cube. And here we go. And I'll read here if everybody's okay with that. When you're ready though, Anne, if you feel the space, why don't you begin reading sometime? I'll start right now for now. Next, we split the octahedron in half, separating the two square-based pyramids. The two additional perpendicular slices divide each pyramid into quarters, producing 8 sections or octants, each with a volume of 1/2. A volume of 4 divided by 8 is equal to 1/2. Each octant is an irregular tetrahedron with a unit length equilateral base and 3 right isosceles triangle sides. The perpendicular corners of the 8 octants meet at the octahedral center of gravity, or the orthogonal relationship first noted in the previous chapter when IVM vertices, body center, are added to cells in the IVM. So this is a little picture of unwrapping the hidden octahedron from the tetrahedron. And now we're on the next page. And this shows a picture of each of the tetrahedra, the 4 irregular tetrahedra that come out of the center of that. And there they are there, the derivative of the octant, 1/8 of an octahedron. To confirm the octahedron-tetrahedron volume relationship, we place an octant with its equilateral face down next to a regular tetrahedron on a flat surface and observe the altitude of the octant is exactly half of the tetrahedron. A second octant can be put on top of the first to check. The height of both octants together is equal to the altitude of the tetrahedron, as shown in figure 10.6. Cool. That kind of relates back to the other picture that was shown on page 166. And I think I'm going to go back there just to see if we can get that page up. No, I'm not going to be able to. Let me see if I can do it this way. Multiplication by division. Yeah, multiplication by division. Yep, here they are. So this is kind of showing the same thing, where the height of this is 2 tetrahedra tall. 1 tetrahedron, 2 tetrahedron. So when we divide this into its parts, it has that height. So.
Yeah, and this other diagram is showing a irregular tetrahedron.
Right.
But it comes up with the same result. The height is double the 2 irregular tetrahedrons.
Right on. To reconfirm the octahedron-tetrahedron volume relationship, we place an octant with its equilateral face down next to a regular tetrahedron on a flat surface and observe that the altitude of the octant is exactly half of the tetrahedron. A second octant can be placed on top of the first to check the height of both octants together is equal to the altitude of the tetrahedron, shown in figure 10.6, which is right here. An octant, therefore, has the same base and half the altitude as a regular tetrahedron, reconfirming that its volume exactly half of the volume of the tetrahedron. In structure and any comments or questions about this? I'm kind of believing it. I'm just going for it and saying, okay. In structure and pattern integrity, we discovered that a regular tetrahedron fits inside a cube, and subsequently learned that each of the 4 leftover regions is equivalent to the portion of the octahedron from one face to its center of gravity, Chapter 9. We now take advantage of the recently disassembled octahedron for an experiment. Having equilateral triangles in common, octants can be superimposed on each face of a unit of a tetrahedron. One by one, 4 octants surround and thus obscure the tetrahedron. Lo and behold, a perfect cube emerges. Figure 10.7. 4 octants with a combined volume of 2 units that have been added to the unit volume tetrahedron for a total of 3. Compared again with the irregular volumes listed in table 10.1, generated by the unit edge cube, these whole number ratios for the cube and the octant seem especially remarkable.
Yeah, that's quite exciting to be able to, really picture that now with the idea of you start with the tetrahedron and put the 4 octants around, and bingo, you've got a cube.
Yeah. And I would have never actually thought that. There's the table. Table 10.1, it's on page 163. But the tetrahedron has a unit of 1, the octahedron has a unit edge 4, and the cube has 3 unit edge and a unit diagonal of 1. Okay, cool.
But if I look at number 7, 10.7 again, in terms of how that octahedron or the cube was formed, am I seeing it correctly that it's just one tetrahedron, if you want, now inside the cube?
Right.
And not 2?
There's only one tetrahedron inside that cube, and each of the 3 faces have this irregular tetrahedron from the octahedron.
Yeah. So again, would that mean that the tetrahedron, or not the tetrahedron, the cube is, if you want, partially stable? It's still got flex in it that's could disfigure it if you want.
I think if it has a tetrahedron in it, it's not going to be unstable. It's going to be stable because it has the cross members.
But only half. Like this is again, I'm coming back to whether or not you need 2 in order to really stabilize the cube, or whether 1 is enough.
I think 1 is enough because this tetrahedron right here is not going to crunch. It's not going to collapse. It's like when you take a house and use a cross member, put the diagonal on a house, that house is not going to fall over.
Yeah.
And there's 1 tetrahedron there. Okay. Any other comments or questions? Manu.
Look at this.
Okay.
Here, let me just put here. You see the XYZ?
Okay.
See if you can capture that and show.
What's that?
Capture
Move it just a
this.
little bit. Move it to a little bit to the left. Move it over to your right. There you go. Move it a little bit closer. Whoops. And now move it to your right just slightly. To your right. A little bit more, please. A little bit more. Okay, that's good enough. I got it. Here it comes. There you go.
Okay. You see the XYZ?
Yes.
at right angle each.
So
You
this
see
must
the
be a-
yellow? Yes.
This is an
The
irregular
yellow.
tetrahedron.
Yes. No, just look. You see the yellow, the orange, and the green faces.
Yes.
The three faces of the XYZ. Now, those triangles are irregular, right? They are right angle triangle.
Right.
Yes, I said they were irregular, yeah.
Yes. Now, you see the contour in red.
Yes.
Is it regular or irregular? In other words, is it equilateral or not?
It looks like it's equilateral, possibly.
It is equilateral.
Okay, good.
Those are the diagonals. So that's what you see, the phase that you see. So you have 1 for 3, right? 1 for 3. One regular face and 3 irregular faces. The 3 irregular faces are the faces for a cube. In order to close the whole stuff, the whole stuff, you need 2 tetrahedra. If you close, or 2 triangle, whatever, if you close it, you have 6 irregular and 2 regulars. So what does that mean to you?
Explain what it means.
Okay. It first means that the cube, as it exists, as a unit of measure, is less effective. Six to 2. And notice that 6 divided by 2 is 3, which is a 3-dimensional of a cube. In order to knock the cube, you have to close the face of a tetrahedron that is knocking out a dimension of reality to have the reality within the cube, or to count accurately within the cube in XYZ. That's the point I wanted to show. And that's why I always say that derivations of a system, you don't need to go more than 2 derivations. That is more than 2 divisions to describe the whole universe. A universe is the set of rational numbers. That's what you call universe, how we can see it rationally. In order to see the irregular, you have, and then you have it, you have the 4, and you take the 2, because there's always duality, this 8. The 4 of the 4 triangles are of similar, we love similar volumes. So one quanta, Bucky called of a quanta of energy. One quantum energy in 1/8 of a tetrahedron, and is made of 2 regular and 6 irregular. And you come in the real world, is made of 1 and 3. The 3 we always see in 3 dimensions in our real world. We can see when we look at this, a volume in 3 dimensions. And we tend to ignore the sine one, that is the sinus one, that is the equilateral triangle that you see there. That makes regular, because it is sine. It is another phase of a reality that we come to realize in truth. So we tend to live in a real world of 3 dimensions by thinking that we are separated from what we are observing. And we tend to ignore the one that is the complement to make a whole that is hidden from us.
Okay,
So,
you said a universe.
so we tend to ignore that window, the 4th window, that enclosed everything in the form of a pyramid, in the form of a tetrahedron, be it an irregular tetrahedron. Do you see that if you take the three irregular plus the closure, the trace of a closure that is regular, you close the system into a 4 dimension. But in order for us to realize it, we have to ignore the dimension that is hidden and only see the 3, that which we see anyway, by turning 3. And it's because we are ant on a plane in 4 dimensions. We can only turn on the surface like this. So we just see 360 degrees. We don't do this. We don't go to the North Pole and come back in the South Pole. We turn on the equator and we see the Earth and the picture of it by the revolution of the sun. That was my contribution here. I hope it hasn't confused things further.
Well, cool. You said that a universe is a set of rational numbers. Why
The
can't
universe is a set of rational numbers.
Yeah. Why can't the universe be a set of irrational numbers?
Because it wouldn't be defined. In order to close the system, we have to invoke a transcendental number, that is pi. That is the 4th dimension that we close in order for us to make sense of the sphere. Notice that pi is not irrational. Pi is transcendental, it's further than irrational. Irrational exists, that 1 divided by 3 exists. We can divide rationally something in 3. And the third of it will be one number that never ends. But it's a number like 5. That is, you can build it by adding proportions that are clearly palpable to get to that result. But you cannot add any of the rational proportion to define pi or to define exponential, the base of a logarithm, the natural logarithm. You cannot, because you have to invoke the hand of God. I cannot live on my own. I need my God. And that my God is in my system defined by the transcendental number that I choose. Same for logarithmic counting. I need a base. You cannot count without a base. What is the base? Is E. 2.721, infinitum is transcendental. Transcendental means that it cannot be defined by the parts that you have within the system. You need to go out. In economics, they call it the invisible hand. The invisible hand helps the prices to stabilize into something that is observable by everybody. In a supply-demand theory or market, whatever, you need to invoke that one. Okay.
Okay, good.
Let me just add something based
Please.
off of our earlier discussions, I think last week with the Leonardo.
Leonardo da Vinci.
Yeah, I'm sorry, yeah. And we were introduced to the tetrahedron constant at 1.633. And we were looking at it in terms of the pi at close to being a constant, but not quite, and close to being a sort of 1.6, but not quite. And we were intrigued with the idea that the tetrahedra number is constant, and the other number is close, but not quite. And so it also brings us into the dialogue about whether or not something like a tetrahedron constant, just like the phi number, is a number that needs to be given more attention or more understanding or more awareness. And so almost we have to learn to talk about the tetrahedral constant either alongside as we transition over to it, or to recognize that one is still kind of flexible, it's approximate, and the other one is more of a firm constant. Yeah.
Yes, Richard. Remember this. When we talk about the tetrahedron constant, we are reducing everything to the matrix. That is to the vector equilibrium. We're just looking at the edges. We're just looking at the vertices, and we're just looking at the faces. Pure, 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 pure. We're ignoring the dampener, the phi. Now, phi, we know that in the duality role, in the duality function of it in the system, phi is like on the note. I'm not a musical player, but this is that thing. And Steve's fingers, they go like this. They hold here, they hold here, they hold here. They dampen the frequency of this guy here in order to produce the expression of a structure here in the spaces, the musical expression of a structure. In so doing, it will never be perfect because the phi introduce the function, the friction at the border. So the measurement by estimation that we saw in the natural, and remember that the organic thing is always the association of a matrix and the phi. I repeat, the organic thing, that is the living thing, the expression of this is always the dual association of the matrix and the dampener. The two always go together. So when we talk only of a matrix, that is in the tetrahedral ratio constant, we're ignoring the effect of the boundary on the whole system.
Yeah, I understand that, Manu, and I appreciate what's always been talked about phi, and we've certainly been talking about that in cosmometry. And it speaks to, if you want, the fluctuation. But I have never seen in that whole kind of discussion around phi a recognition of the tetrahedral constant and what the difference is and why it's important to have something like phi. That's what I'm getting at.
Yes.
So it's been a one-sided discussion to get at the notion of that dampening or the flux.
Yes.
And that's what came out of the reading of that article last time, was there's two of them. And when you get the two together, then it's much easier to have understand the explanation that you just gave as to what's the difference between the two numbers. And it becomes very, very important. But all I'm saying is that that article was the first time I read something that was called a tetrahedron constant.
Yes. Yes.
So if we're talking about learning and progressing, then we have to learn to talk about the two constants and why one is a little bit different than the other, and why one is important for the music or the harmonics or the dynamics to exist, because it kind of goes back to what you were trying to say earlier about the tetrahedron. When it's closed, it's dead. And I have never heard of the tetrahedron being described as dead in the way in which you described it. So I need to have a greater dialogue to get that into my head. because you were pretty definite about that's dead.
Okay.
And I've always seen it. I've seen it dead in the way that we can model it, which I've done as well. But I've also looked at in the tensegrity sort of side of all this is that the lines, if you want, or edges or the connections in between are not dead. They're
Okay.
they're
Let me put it
dynamical.
let me put it like this, Richard. Eternal stability is what? Is death. Eternal stability is death. Life is energy in motion. If something is eternal stability is death. So one tetrahedron, if you talk of one
Just hang
tetrahedron.
on, just hang on to that. Just hang on to for the moment, because
Yes.
this is exactly what and again, I almost get afraid to say I have a source, but my source is chaos theory. And what I learned in chaos theory about equilibrium is that ultimate equilibrium, ultimate stability is dead. And it's the example that was given is the flat line on a heart monitor. And
Yes.
not the ultimate, but the ideal, if you want, equilibrium or stability is far from equilibrium, far from dead. It means it's really dynamical and robust. It's got stretch and fold and all the things that we've been talking about. And
Hold on.
well, not just and this was a great learning for me to get away from the notion of equilibrium is a balance between inner and outer forces, and that kind of equilibrium to me is dead. It's static, and yet
Okay.
that's what
Let me explain.
what
Let me
just,
explain further.
so that's what I have discovered was the problem in some of our social situations where you say you have to get the balance between work and play or work and home, and it comes across as if you have to get a stability, a flatness. But the understanding that I got from this other area says, no, you want stretch and fold, you want movement, you want the opportunity for people to expand and contract and all that kind of stuff. So that's where I'm coming from in terms of different understanding of equilibrium.
Okay. So
And
I say,
stability in that sense.
yes, one tetrahedron is dead. One. Two tetrahedra is alive. Let me put it in a social context. Social context is a dynamic of relationship. If you have one individual in that social context, is there any relation? That is a single element in the whole set. Nothing. Is dead socially. If I live in isolation, this is pure mathematics. If I live in isolation, complete isolation, I'm dead socially. So one tetrahedron is dead, is ultimate stability, everything, is the IVM. The IVM is dead. You need a strike of IVM to create life. You need a boundary. You need the first division. You need something to strike it, to kill a system. We had the world of dinosaurs. That was a world that was thriving. Or for an external person, the world of dinosaurs was dead. But it took the strike of a meteor, was it a meteor? That hit it and created this volcano, that created this fume, that created the cold, and the world of dinosaurs disappeared. The whole Cretaceous disappeared and gave rise to another form of life. That's the context in which I'm talking. we've seen, I mean, even Anne said it or somebody said it. If you look at the IVM, you look at the same thing in all directions. What does it mean? Does it mean it's alive? It is ultimately stable, but it's dead. It's made of triangles that concatenate with octahedrons. Yes, it's made of triangles that concatenate in a way that is rigid like this. You need voids inside it. The appearance triangle. You need the voids of the cube for it to start doing this, or doing this, or doing this. That's it. You need a mantle of the earth for the cross to slide on it.
Well,
I mean, I'm not.
Well, I guess the other thing that's important for me right now is when you say you come from a context, and that's valuable. And I think it's possible that we all come from contexts that may or may not be exactly the same. And that's what we have to appreciate, is the context sometimes has an impact on the interpretation. So I appreciate what you're saying, especially in you talking about the context. And I've coming from a slightly different context, but I think it's, a lot similar, but where the tetrahedron by itself, in that kind of concept, can have the lines in between the nodes that are in motion, or their movement. And so
Yes.
that tetrahedron by itself is not dead in my context. That's all.
Well,
Okay.
it is, if it is, to say, let me just put it now, first thing. 2 points. Marginal, point marginal, is that the beauty of the context is what creates angles of observation.
That's right.
But the building of truth is that we're going all to the same direction. It's teleological. We live in universe, whether we want it or not, teleologically, because universe has a destination. It's not just there like this. Universe is a vector going somewhere. It is expanding, for example. That's the first thing.
Okay.
The second thing is in regards to the I was going to say, Richard, can you repeat your second point? It was in relation to the second that you said.
All I'm trying to say is context is very important. And
Exactly.
context is the way in which we will see things, experience things, describe things. And it is a different angle.
Okay.
That where you come out of your context to sort of explain something. The problem that we have, and I'm meaning a general royal we, the whole world we, is that sometimes we come out of a context, and what we see we interpret as being absolute. And the big struggle is to appreciate the contexts, and then we see methodologies, or we see different interpretations, and there isn't necessarily one fixed answer. That's all. So that's what I was trying to say.
I got my second point.
Well, did you understand what I'm talking about in terms of context?
Yes.
Yeah. Okay.
The second point is this one. If I take this, it is dead to me. Because I press it, it doesn't go anywhere. It has a resistance to the pressure of life. Death can also be defined as absolute resistance, impedance to the pressure of the flow of life around us. you are dead. Okay. At some point, death and a point of life, they meet somewhere. Because I can be like this. You can also conversely or convexly say that there's a lot of life inside. There's lots of life, so is living. So death and life, depending on whether you are talking of it from the concave point of view or from the convex point of view, mean the same thing. Second thing, if I take this ball, look at this ball, it looks solid. It looks like if you were like this dead. But, and we all agree that the energy that is in here is finite. That one is finite also. But look at this one. Why does it do this? Because there are voids into this one. There are voids. Remember that when you squeeze something that is locked into a closed boundary, you squeeze it, you cause energy to go from the high, the most expensive, to some low point. Flow of energy. This is flow of energy. And the universe does this. Tetrahedron, octahedron, and icosahedron. Tetrahedron, icosahedron, or vector equilibrium, that way, does this. It is pulsative at a rhythm. That's why we have patterns. That's why we have lines of flow. It's because of this motion. So at the origin, you need the two poles. What created the whole world is two poles. Is a force coming from outside and striking another one like this. And then relaxing. That's that. That's what has been created. It did this the first time, and all the remainder is a fractal of it. It is expanding, dividing, doing this. That's life. Do you see it on your screen? That is life. So to have life, you need two. You cannot talk of life in one. Life Bucky say, life starts with awareness. Awareness of the otherness. That's what it means.
Cool. I have an issue, and
Okay.
that is we're beyond our appointed time. And I've had real difficulty trying to figure out when to jump in on this thing. So, Joe, were you able to attend much of the call at all?
I was on for the first 30 minutes, about,
Yeah.
and then obviously the last 20, roughly.
Okay, good. Well, do you have any takeaways you want to share and you want to pass it along?
Sure. I mean, it's still good to be on the call and listen to the discussion. Sounds like I did miss some really key points. But that being said, you know, the multiplication by division is one of the most important concepts to understand. You know, especially from my perspective, in the sense that a lot of times when people build things, they just add things on continuously, and that's where you know, if you're thinking about it in terms of like even a battleship or the Tesla car or whatever it may be, it's the simplification that enables something to be more efficient. And that division and that more efficient use of energy is, you know, it's essential to things like ephemeralization. So, so it's a really important concept, and you know, I look forward to you know, getting a little bit more deeper into it next weekend. So, Anne, how are you doing? It's good to see you. how do you feel and what are you taking away from today?
You need to
You're on
unmute,
mute.
man.
You're on mute. You had a great smile though.
Yeah.
Thank you, Joe. I'm so happy to see you that we can see you. Okay.
Yeah,
Over the
I'm
past
happy
few
to see
weeks.
it as well.
Yeah. Yeah, I'm actually getting a headache because wow, over the things that need to change. Now the headache is a good headache, yeah. It's about how do we get this all the way down to fixing it and then to get the actual information down to kindergarten level, right? Because so much of the information is incorrect, yeah. The way it is already, we are fixing some stuff because facts are off when it's introduced at kindergarten level because most of the teachers do not know math and physics and all that to that level, right? So things, a very simple one like tomato, what is it? You know, majority of people in Malaysia, like for me, I grew up thinking of it as a vegetable, right? But it's a fruit because if you look at it by definition, brinjal is a fruit, cucumber is a fruit, it's a fruit, yes, and so on. So math, we were fixing it too, right? And but there's a lot that needs to go all the way down to the ground, and that is massive. So anyway, I'm gonna be for me, the excitement has been listening to and picking up so much. My people are starting to think in the same way, and the words are popping up in phrases that I mentioned. But now I realize, oh my God, what we're talking at this level, how do we get this down all the way? Because there is nobody in Asia that is going to know what we're talking about. And you're talking about hundreds and thousands of teachers on the ground. They need to get the right information, right? And that's just one country. Anyway, this is something for me to sit with. And yeah. So Lee, how do you feel? And what is your takeaway today?
Lee, are you unmuted?
I can't. My phone is so low.
If you're on, you can talk. Find your button and just put it on.
I've been hunting for the whole time.
We can hear you though, Lee.
Okay, what you gotta do is you gotta get out of there. Out of there, now touch the bottom.
Okay.
No, you touched the wrong place. Touch the bottom right over there. Wait a minute. Okay, now touch it. Well, I'll touch it now. There you go.
I'm unmuted, thank you. I have been puzzled 90% of the time of this conversation between all of us talking, and I don't know math at all compared to you guys. This has been a difficult class for me to be in, or meeting to be in. But I can see with the diagrams what all of you are talking about. And I'm excited about it. And I see tetrahedrons everywhere. And triangles, squares. And in a square, I can see all the tetrahedrons and triangles in it now compared to what I used to. And it's been really wonderful. I think that, now did Manu have?
No, you can ask Manu.
Manu, what do you think
How do you
of,
feel?
how do you feel about today's, all of the talks?
And what are you taking?
And what do you take away from it?
I'll thank you, Lee. really, I'll begin first by apologizing that I can be sometimes rash, but it comes from the passion, and that passion is limited to this call, the context of this call. It should not and must not translate outside of this context. Meaning that at the end of a call, we still friends, we still brothers and sisters. That's very important to me. So we lock horns, but we still bulls. The second thing that I have is that I recognize that we are sentient beings. Sentient beings mean that we perceive the world around us through our senses. Inherently, it is imperfect. And everything happening because of something, nothing happened for nothing. Everything happened for a reason. Sooner or later, that is with lag, we or some other being will realize that that sense that we have, the way we interpret it, is incorrect. Unfortunately, in between, we interpret it falsely and it has really consequences because we work with that. We do energy and it creates heat around us and it hits the place unnecessarily in a direction that it shouldn't be. That's the second point. So repetition by learning and doing is the mother of all progress. Now, coming to universe. Universe to me means same interpretation by insiders.
Say that again.
Because universe to us is same interpretation of what surrounds us by us who are all insiders of that universe. Because none of us, except through his mind or her mind, has ever ventured out of it. We are all locked into it. Having accepted that, notions and definitions recognize their limitations, their context. And inspired of us, that is, we want to appropriate things, as Richard said, we should remain open. Because what we're certain of today is more than likely something that is not absolutely true. That's why the dynamic and the fluctuation of the boundary of a space of cognition of universe. Third, universe being what it is, we should recognize the fundamental principle of duality. Meaning that I can't see one thing only. There's always, there's a face, there's a tail. Let's just put it simply like that. To anything that holds a volume, that is a quantity of energy, a quantum of energy that is held by a recipient, that recipient has a face and a tail, at minimum. We will say has a face, a tail, and the edge. And to be able to observe, to know what is going on, to shorten the lag of information that arrives us, the best position of us is to be on the edge. If you see a lizard on a roof, the lizard doesn't prefer to work on the crest of a roof, on the ridge of a roof, because the lizard can do this and that, do that, seeing what is left, what is right. Let's recognize that it's most difficult to be on the edge, at the boundary, because that edge is sharp. That edge is rough. So in the quest of our seeking to understand our surrounding, we should be develop the ability to expand, to go to the boundary, and the flexibility to go quickly like this, left and right, left and right. And the so-called quantitative theory or whatever is only the frequency side of things. We have computers that compute many things at the same time. We have divided many times, they become complex. Because every time that you divide, we saw that there's a relationship, because there's an edge every time that you divide. So as we divide more, there is a complexity of stuff. But by looking at those complex systems, can never kill the fact that there is the amplitude side that is hidden. That is the observation, the ability to be able to see patterns. Amplitude is again patterns. It is additive. Amplitude is additive in that if I have one amplitude of this quantum and I take a second amplitude of this quantum, I add to it, it is 2. Right? When I blow air in a balloon, if I blow one volume and I blow a second volume, the volume of the balloon is twice. But when it comes to frequency, that is the number of turns. That thing is on the square. 2, 2, 2. It's 2 to the power of it. It is spherical. So, I don't know if any of you saw in what Steve showed there, I wrote Kelly's formula of your effectiveness. That says, Kelly has developed a formula that he says in 20 years or 30 years, nobody has been able to disprove it. He cannot demonstrate, but it is true so far, is that minus gravity, minus means getting in. The convention is when it's plus, it's going out, it's dividing. When it's minus, it's coming in. Minus gravity, then radiation plus. So in, out, a system. Gravity, radiation. Multiplied by the symbol. The symbol is amplitude or pattern. And note that patterns are additive. Divide by the focus. Focus is the macro, is frequency. And that divide, the focus should be, frequency should be square. Because you're dividing, you're taking a segment, and you're looking at Steve show that segment in a sphere like this. So it's radius square to that surface. Gives you your result. So the focus is on the denominator, your microscope, and the amplitude is on the numerator. And this formula shows that the two always go together. It is a division though. So you're multiplying by dividing, and then you integrating. So the pattern is also what Kelly called a symbol. Identify a pattern. Now, when you see a pattern, that pattern happens and disappears because there's lack. That's the pulsative nature of universe. That's the pulsative nature of our living in the universe. That's the only tool we have. We have a tool of dividing. When we divide, there's one that we can see, the other one that is hidden. We call it, the one we can see, the concave, the pattern that we see, and there's one, the sign of it. Because what we see is the cosine. The sign of it is hidden. And to me, I always try to hit at this. I hit at this, I hit at this, I hit at this all the time. And coming to Richard, in the social context, and we saw it, I want to repeat it. We had it last week, or we had it on Wednesday. Agreements in the social context are edges. The process Processes is the exchange, is the faces. So agreement are edges, processes are faces, rules are purpose. Because rules, they are vector that take you to a purpose. Where is it going to? So it's the polarity of a system. The rules is the polarity. And then the people and the participant is vertexes of that system. That's something I had from Wednesday, discussion on Wednesday. And the last thing that I'd like to show is a description of a world from Becky, and starting from a segment, awareness, a segment. So we saw that if you take a segment and you divide, you have 2 segments. If you divide again, you have 3 segments. And the 3 segments you can close, that is, you can introduce an angle to determine a triangle. And that triangle was of dimension 2. Why? The edges were 3 dimensions. And since you should not talk of a triangle on its own, you have to multiply by 2 nah? To do something. And that describes once you do another division. That is, now you have defined these 3, the orthogonal system. These 3, we saw that 1, 2, 3 at 90 degrees, dividing like this at 90 degrees. You have these 3. Then you have a cube. But in order to see the 4th dimension of it, we needed to cut the cube, like to take a cube and cut it diagonally like this. From this end, right, from 1 vertex to 2 vertices, that plane, that hypotenuse plane of the cube, the diagonal plane of the cube. Once you do that, we saw that you have now 4 dimensions. 3 are right angle, and 1 that is like a base of a regular tetrahedron. Now you have the 4 faces. That one that is the base of regular tetrahedron, remember that is the pure sign and it's always hidden. We need, in order to see it, we need to expand our mind to the boundary outside of the 3 dimensions, 4th dimension, and be able to see it. I'm true, I have other things. I hope I wasn't pontifying, but I hope that what I say helped, and I wish it didn't confuse more. So I'm grateful for all. Sorry to take much time in trying to explain this. Who is left? Richard? Richard, how do you feel? What do you take away?
I don't know. I guess in some sense I feel a little bit conflicted. But what I kind of take away, I think, more than anything else, has to do with 3 words: dialogue, context, and angle. And I think being able to sit in, if you want, my own context, and also, in a sense, sit in the context of others, and the angle that we see things and how we explain them or describe them, make a point, shows us how extremely difficult it is to be in dialogue in the emergent way that David Bohm talked about, and allowing each other's context to sort of be visible and around us, and each of our ways of trying to understand, but then also appreciating the dialogue of there may be something that's emerging out of other people's contexts and angles that I hadn't seen, and I should take into account and I should think about. So that's my big takeaway, is, again, understanding dialogue in context and in the angles in which we see and experience things. And it really does come to something that Anne was talking about in terms of how do we get contexts down into the context of a 6-year-old or a 5-year-old, so they can begin to have their own angle on it and have their own expression of what they feel or see or thinking about. I think that's a huge challenge, and I think that's what we get into from time to time is that we sometimes get our context trying to override somebody else's context. And it's hard to kind of back off from that at times and get back into the spirit of the dialogue, which may emerge in something that we didn't see or know before, and we now want to make it part of our own awareness and understanding. So that's my big takeaway is those three things. Over to you, Steve. How do you feel, and what's your takeaway?
Well, I'm frustrated because, do you want to put your phone on mute? We're half an hour over this call. I'm supposed to be conducting the call, and you address issues of dialogue and perspective and point of view. And I have certain ground rules that I feel I'm obligated to in order to maintain the integrity of this call. And one of those is being able to end on time. And I have a feeling that if I were to have interrupted at any given point here to end on time, I would have broken somebody's rant. And as important as the rant is, I break the ground rules. So I've got to take a look at what ways I can facilitate having more dialogue, and doing what I can to keep the perspective of the book, to keep the perspective of each of us that we bring to this conversation, and then the desire for new knowledge and new perspective. Manu, I love your enthusiasm, and sometimes your enthusiasm, in my judgment, gets in the way of my ability to hear you because I feel like you're contradicting and arguing. My problem. And I think this goes to the base of what Anne is talking about in terms of, yeah, we have students we have to worry about in terms of how do we teach them the world the way that it really is. But I think Anne's biggest problem is getting teachers and administrators and the public who are funding the operation to support a point of view that doesn't support amnesia and that does support dialogue and that does support different ways of looking at things while it respects the truth about a thing. Because my perspective is important, but it may not relate to the truth in the context of the group. So that's a big job. I had a breakthrough tonight in terms of when Manu was talking, when I was able to hold up these sticks here and then broke them into two and then broke them into three and then built the triangle and then divided the triangle. And that was wonderful to give me a two-dimensional understanding of some of this stuff. For me, I never understood until tonight the idea of how I have to divide in order to multiply. I mean, if I give a kid a toothpick and I say, here, create two toothpicks, there's only one way to create two toothpicks, and it's by dividing it.
Yes.
It's only one way to do it. You got to divide in order to multiply. There's no other way to do it. I can theoretically say, well, I simply take this number and I multiply it by that number, but that's an abstract mathematical concept that doesn't really deal with reality. It's an artifact of the way I perceive reality. And this is reality.
Yeah.
So that was big for me, and I'll probably hold on to that and do what I can. And I'm going to ponder my commitment and responsibility to maintain dialogue on the call and maintain our freaking boundaries. We're a half an hour past our time, and I want to thank each of you for being here. For Joe right now, it's 1:30 in the morning. You know, So thank you, Joe, for your persistence. And all righty, so I'm complete. I see a few comments in the chat over here. So make sure that you see those, and then I'll send out the recording with the chat for our next week's call. Peace until next time we meet.
See you guys
Bye-bye.
soon.
You bet. Somewhere in here is the.
Where is the exit?
My buttons are not easy to find.